Okay, so let's talk about how to find the pH of a weak acid. A couple things. The first thing that you'll need is to really understand if you are looking at a weak acid or not. So remember, you have your list of strong acids, and if it's not on that list, then you would consider it to be weak. You're going to write a balanced equation for the weak acid in equilibrium with its conjugate base. You'll write your Ka expression. And then you should be thinking that you're going to need an ice table because you won't know the percent ionization. And then number 5 here is an important one. Let me get my pen right here because we also want to double check if there's any way that we can simplify the calculation so we don't have to do quadratic. So let's go ahead and take a look at one. Here's find the pH of 0.10 molar acetic acid. So acetic acid, not on our list of strong acids. So it is a weak acid. And let's go ahead and write its ionization equation using Bronsted-Lowry. So here's the acetic acid plus water in equilibrium with its ions, H3O plus and acetate. So this Ka value is either given or is in your book in the back. And one of the first things you should notice about the Ka value is it's pretty small. And so let's set up our ice table, and then let's talk about any sort of assumptions we might be able to make. So we have 0.10 is our initial. We do not know how much is ionized. And so that's initial, your change, and then your equilibrium. So 0.10 minus x, x, and x. Okay, so our Ka expression, H3O plus times acetate. Since we're always losing one proton at a time, the ratio is 1:1 on these, so that makes it easy. So there aren't any squared terms. Then this will be x squared over 0.10 minus x. So setting it equal to our Ka, 1.8 times 10 to the negative 5 equals x squared over 0.10 minus x. Okay, so when I'm looking at that, based on years of experience, I can tell you that our Ka value is small, and our initial concentration of 0.1 is not super big, large concentration, but not super tiny either. So I'm hoping that we won't need to use quadratic on this because that's a lot of extra work. What that means is I want to be able to assume that this x is really small compared to the 0.10 so that that term crosses out. So the one thing that you should do for that is do an assumption, or I should say, how about we call it a shortcut? Give me a second to grab my calculator. Okay, we're going to take the concentration of the weak acid divided by the Ka. And if that ratio is greater than 400, we will not need quadratic. So let's run that through for this one. I'm going to click on to the next page if you don't mind. So I'm going to take my 0.10. So that's a really big number. and that is much greater than 400. So what that does for us, if we have our Ka value and equilibrium expression, what it means is I can ignore this x. And notice how much easier that's going to make our lives, because x will equal the square root of the Ka times the concentration. And I will get 1.3 times 10 to the negative 3 molar. And that's going to equal our H3O plus concentration. So the pH then will be the negative log of that value. And that will equal 2.98. So let's talk about the percent ionization for a second. That's going to be the amount of H plus over the weak acid. So what percentage is it? And so we're going to take our X and divide it by the original concentration times 100. Now, here's some interesting points then, and I think really important. Since this percent ionization is less than 5%, we know our assumption in ignoring X was valid. Meaning that the acid isn't very ionized, and so we could make this assumption, and if I can get up there, oh my goodness, that's brave of me. We can feel comfortable that we can cross that X out, okay? And then this shortcut, I know seems a little random, but it's really based on looking at this assumption that it's less than 5%, and so this number here will be greater than 400 when that's true. Now, what does this mean is that the closer we get to 5% ionization, the more likely you should run a quadratic, okay? And the more likely, so if this was, let's say, a 7% ionization, then this number wouldn't match what you'd get with quadratic equation, okay? Now, one other thing is that a 0.10 molar HCl, strong acid, its pH is the negative log of that value, which is 1. And so do you see such a big difference in pH? The pH for the weak acid is 2.89 at that concentration, whereas the pH for the strong acid is much lower. And that's because the strong acid's 100% ionized, and the weak acid's only 1.3. So if I was to say, or pick an important calculation for all of Chem 201, it's to really understand how we calculate the pH of a strong acid and weak acid. And you have a lot of homework assigned for this. It's also on your take-home quiz. And I'd really like you to learn it well. Those of you, there's always a few students who really enjoy quadratic. They have their calculator set up to do quadratic very easily. That means if that's you, you can always just run the quadratic. But the simplification is important as well in terms of conceptual part, that when this number, the Ka, is very small, the smaller it gets, the more likely we are to be able to ignore that X. So here's another sample problem with propanoic acid. A couple comments. Some of the acids get more complex, And what they're going to do is they're going to give them to you as simplification. So propanoic sometimes is written as HPR. If they're going to do that, they're going to tell you. It has a Ka here, kind of similar to our last Ka for acetic acid, and then the same concentration. So right off the bat, what we would want to do is to do the same thing we did, which is to take and figure out if we're going to be able to use that simplification or not, whether we're going to need to use quadratic or not. So we're going to take the 0.10 and divide it by the Ka. I'm plugging it in. I get that's much greater than 400. And we say, yay, X will be very small. And this part here is saying the same thing, but it's just saying that if Ka is small, it's going to disassociate very little so that we can ignore X in that bottom part. It is not showing you this shortcut that I'm showing you though. I think this is the best way to go. So here's a nicer looking one. Products over reactants. Set up your ice chart. Very similar. And then since Ka is so small, we will assume that we can ignore that X right there. And you see how that's what they've done here. So rearranging this, you take the Ka times 0.10 and then take the square root of that to get H3O plus. The percent dissociation, I'm calling it ionization. Please make sure you realize they're synonyms for each other in chemistry. So the H3O plus divided by the original concentration times 100 is a 1.1%. Notice that it's less than 5%, so we can feel good that we didn't use quadratic. So quadratic was not necessary. This is a conceptual question for the next part, and this is something you're going to be exploring in your lab for pH and buffer. The percent of dissociation or ionization is how much has disassociated and how much you have initially. So I like to do this more as this is H plus over HA times 100. Interestingly enough, as the acid gets more dilute, the percent ionization increases. So more dilute solutions, we see an increase in percent ionization. Kind of opposite of what you might think. You might think that if it had more acid in it, it ionized more, but it's actually the more water you have, the more dilute it is, the more the acid's going to ionize. Okay, so that's going to be an important discussion for your pH and buffer lab. So just remember that. You're going to have some data and you're going to show that and look at that experimentally. Okay, so what this is really trying to get you to think of is just the last one, the last concept. Here we have a 0.40 molar HClO and a 0.035 molar HClO. So this is hypochlorous acid, and it is in equilibrium. So we can write out its ionization with water. reviewing, this is our weak acid. This is its conjugate base. Now, based on our previous discussion, what we should see, just looking at the numbers, is that this should have a higher percent ionization because it's more dilute. And let's see if the numbers support that. So I'm going to skip this one. So here is the one for the more concentrated one. So this is more concentrated. Set up our ice chart. Let's see the shortcut. So we're going to take 0.40 divided by the Ka, and I'm going to crunch that number. Give me a second. Whoops. Sorry. Give me a second. You can do it with me. So we have a really gigantic number here. So that is much greater than 400. So for sure, we're going to be able to ignore X. So let's take a look at that. So this was ignoring X. So see how it's gone here. Bringing it up, multiplying it, taking the square root. We get the H3O plus concentration. Not a big fan of how they write it. And then putting that into there, we see a very, very small percent dissociation. Okay, 0.028%. So for sure, our shortcut was valid. Okay, for the other concentration, the 0.035 molar, running through the same exact procedure, what you notice is that the percent ionization ended up being 0.091%. So we have a higher percent ionization in a more dilute solution. Okay, so let's wrap up by talking about weak bases. And in a Bronsted-Lowry definition, a base is a H plus acceptor. And so if you have a base, it's going to accept H plus from water. So in this case, water is your acid. Its hydroxide will be its conjugate base. And then here's our base. BH plus will be its conjugate acid. Okay, so now we have a base dissociation or base ionization constant given by Kb. B is for base. And let's take a look at how the calculations are going to be. They're going to be similar. Before we do that, let's take a look at this. This was that family of bases. So here's our ammonia, NH3. Here is, now remember, here's NH3. Okay, we can substitute out one of these H's for a CH3 group. So this would still have the lone pair on there. Anytime nitrogen has 3 bonds, it has a formal charge of 0. Okay, here, now we've substituted out 2 of the H's for CH3. Okay, and so we have these guys here are all related to ammonia. So if we have, as you see, let's start with ammonia. It's going to grab an H plus, and it's going to form NH4 plus. Anytime you have the nitrogen with 4 bonds attached, its formal charge is going to be 0. Plus 1. So remember formal charge, nitrogen, 5 valence electrons, and then we count the bonds 1, 2, 3, 4, and that gives that nitrogen a plus 1 formal charge. So let me star these ones that are more common for us to use: dimethylamine, methylamine, and ammonia. And the only one not here that I think is also worth noting is CH3, 3N, trimethylamine. And I would say that that's another one that you should consider as you do your homework. Okay. Notice they have KB values, and then there is such thing as a PKB. That's just the negative log of the KB. So I can find where I'm at. Okay. All right. So let's say we want to know the pH from the PKB and the initial base concentration. So here's our dimethylamine. Remember, this has lone pairs on it. It would look like this. Okay. And so it's going to be able to accept H plus from water. Okay, so let's see how they write it out on the next slide. See here, this will have those lone pairs. It's going to accept H plus from water. Over on this side now, this nitrogen will have 4 bonds. That's why it has the plus. And then you form hydroxide. Okay, setting up our ice chart again. This is our initial concentration, minus X plus X plus X. And then we can make the same exact simplification or assumption. Check that number out. And what we would have seen is that we would have been greater than 400. And so that would have been taking the 1.5 divided by KB. And that would be a lot greater than 400. So we know we're going to be able to ignore X. So X now, though, this is very critical. X is hydroxide concentration. So because it's a base. So the fact that we're solving for X, that is hydroxide ion, which means that we should probably find POH. Now I know this shows an alternate route here. Can I gently kind of cross that out? Because I feel like that's too much work. Instead, what I think you should do is take the POH hold up. Which should be 1.52. And then to find the pH, take 14 minus that number. And then notice the pH is really high because that's basic, right? So a high pH greater than 7 is basic. So we should always ask the question, does our number make sense, right? Does it make sense for the solution we're looking at?